Okay, I think we'll begin. So today we're going to be hearing from two students that actually worked with me on research. This is during the fall semester, so it's not done yet, but they're going to present what they have found up to this point. So let's welcome Dory David and Kelly Gray. All right.
Hi everyone, I'm Jory,
And I'm Callie.
and over the course of the semester, we got to work with Dr. Ko and hopes of answering the question, is AI smarter than humans? And specifically in relation to generating our code to make predictions. So before we begin, we're going to do a little activity where we're going to show a series of images, and each slide will have two images, one that's generated by AI and one that's real. We'll give you guys about 10 to 15 seconds to make your guess, and then you'll vote on which one you think is A. We'll start easy.
Okay, so here's our first set of images. Take a look. Okay, so raise your hand if you think image 1 is the AI generated. And image 2? Okay. So image 2 is the AI one. Now we'll go on to another one. Okay, who votes for image 1? And image 2? All right. All right, people who think image 1 is AI and image 2. Okay, so this one's actually image 1. Now we have a fourth set. Who thinks image 1 is AI? And image 2? Okay, so that one is image 2. All right, who thinks it's image 1 and image 2? Okay, so this one is image 1. And then we have our last set. Who votes for image 1 and image 2? Okay, so this one is image 1.
So obviously AI is pretty good at generating images, and this is because there is an entire industry of people who sort through images and they tell AI what's real and how real images are supposed to look. And they've been trained on thousands and thousands of these. And an example would be if we go to our last slide. These people in this industry will go through and they'll look at images, something like the aurora borealis, and they'll tell AI what colors are supposed to be in it, what they're supposed to be shaped like, what the reflections look like in the water, and how the colors contrast with each other. And so in this industry, AI has just been trained thousands of times, and this is really similar to training a statistical model to make predictions. So that led us to wondering if AI is trained well enough to make predictions on data sets better than we could produce on our own.
Yeah, so this is the main goal of our project. We wanted to see if AI is better than we are at making predictive models for data sets. And we also wanted to see how consistent AI is across different platforms at choosing the same model as being the best model for a given data set. And we wanted to see how well AI is at explaining its results and explaining why it thinks a given model is the best for a data set. So to test this, we used two different data sets. We had a medical insurance one and a vehicle insurance one. So we had the medical insurance one, which we're going to be presenting our findings on today because it's smaller, so it's just more simplistic to explain. And we're still working with the vehicle insurance set because it has a larger number of observations. So we're still finding out how AI responds to having more data. And to test this, we used R code to generate statistical models. And we first did this using our own background knowledge to create a model. And then we asked 3 different AI platforms to do this. So we're going to go through our findings. So here's just an overview of our data set. We have the response variable, which is medical charges. So these are just costs that are billed to the beneficiary, so policyholders or dependents. And then we have 6 different predictor variables, which are shown at the top of the box. So we have age of the beneficiary, whether they're male or female, their body mass index, how many children they have, whether or not they're a smoker, and which region of the United States they live in. And this is really the foundation on which we began our statistical analysis.
So before doing any kind of analysis, we had to split our data set into a training and test set. We chose to do a 70-30 split, meaning that 70% of the observations in our data set were pulled out randomly by R, and they were held as the data that our model would be trained on as we built the statistical model, and then the remaining 30% would be held off to be tested on once our model was completely built. So not us or AI got to see the test set until after we were completely done making the model. And at this stage, we also created another variable called folds, where we told AI to do cross-validation using the specific folds that we specified, so that we would use the same folds as AI. And so after splitting the training and test set, then we could start our predictive analysis. So as Callie said, we started our first phase as doing our own analysis based on our previous understanding of statistical models and model building, as well as feature engineering, which we'll go into in a little bit. And then once we had our predictions, we could then move on to phase 2, which was the AI analysis, going through 3 AI platforms, ChatGPT, Google Gemini, and Microsoft Copilot, to see if they could perform the same predictive analysis as we did. And then once we had all 4 of those set of predictions, then we did a comparative analysis comparing our results, specifically focusing on the consistency of AI across the different platforms, as well as its explainability in the results.
Okay, so here's a summary of the model we chose compared to the models that AI chose. So we thought that a multiple linear regression model would be best for our data set. And we chose to have 2 different interactions, which we'll get into what that is shortly. But we chose to have a BMI and smoker interaction, as well as a sex and smoker interaction. And then you can see that ChatGPT had a very similar suggestion for the best model. It also chose an MLR model with one of our 2 interactions. But then Gemini and Copilot had completely different suggestions. So Gemini chose a random forest model and Copilot chose a gradient boosting machine. And these ones did not suggest using any interactions. So you can see that 3 different AI platforms suggested 3 different models would be best for the same data set. So this is an interesting finding, and this is just a current summary. We're still working on this through the end of the semester. So now we're going to go into the human analysis portion of our project. So this is what we did before we used any AI to find our results. So first, we had to start the process by examining our predictor variables, which were those 6 variables we mentioned earlier, and figure out which ones were relevant to predicting charges. And this process is called feature engineering. So one way to determine this is through an ANOVA table, which Jory's going to explain on the next slide. But an ANOVA table basically tells you which interactions are significant. And so an interaction is when 2 variables combined have a different effect on the response variable, so medical charges in our case, than the variables have individually. So for example, with our BMI smoker interaction, that means that when we consider these variables together, they impact medical charges differently than BMI and smoker impact charges individually. So we have a question for the audience, and specifically if you're in Dr. Ko's 313 class, you should be able to answer this. So if we have 4 different predictor variables, how many 2-factor interactions can you form? Would anybody like to take a guess?
Or choose two?
Yes, that's
That
correct.
wasn't a guess.
Yeah, so
Well, I asked him first to make sure.
yes, this falls on combinatorics from probability. So if we have 4 objects and we want to choose 2 of them, there's 6 ways that this can be done.
So as Kylie said, we chose to do an ANOVA table to determine which of the predictors were statistically significant. And an ANOVA table means analysis of variance. And so it produces all of the p-values for each individual predictor, as well as their 2-factor interactions. As a refresher, an interaction is a term used to describe how one variable responds to a change in another when they're considered together. So with this, our only 2 statistically significant interactions were sex and smoker and BMI and smoker. And this means that an individual's sex affects their predicted claim differently depending on whether or not they're a male or female. And similarly, a person's smoking status affects the expected charges differently depending on their BMI. And so, yeah, these were in the green box, what we chose to include in our model. And you might notice that there aren't any 3-factor interactions. And that's because if you were to include 3-factor interactions, it could lead to overfitting, which is when a model fits the training data too well to where it doesn't do well on the testing set and data that it hasn't seen before. So that's why we didn't choose to do any 3-factor interactions in our model. So with the decision of which predictors we were going to use for the charges, we could then build a multiple linear regression model. And this is the format of a typical multiple linear regression model where y is the dependent variable. So in our case, it was predicted charges. And each x value are the different predictors that we saw on the last slide. And then the beta values are the expected change in charges based on the 1 unit increase in that predictor value. So if x was age, then beta 1 would be the expected increase in predicted charges for every year that the beneficiary gets older. And then if we were to have a categorical variable for x2, like sex, the way that R works is it goes alphabetically and it creates sex as a dummy variable. So it assigns a value of 0 to females and then a value of 1 to males. So instead of x2 being labeled as sex, it would be sex male. So B2 or beta 2 is the expected increase in predicted charges when a beneficiary is male. And then our epsilon value is the error term, which is the difference between the model's predictions and the actual observed values. And our model can actually never know what the epsilon value is because then it would be able to know what the beta values are. And so therefore, the job of any predictive model is to minimize the error term by guessing the beta.
Okay, so here is our final model that we came up with using R. So we have our predicted charges, and you can see that we have our 6 predictor variables with the 2 interaction variables. So you can notice that the orange numbers, those represent like the slope for each of the variables. So for example, with the 267A, that means that for each year a person increases in age, we would expect their predicted charges to increase by $267. And then you can also notice the sign of each slope. So for the sex male variable, as George said, if someone was a male, that variable would be assigned a 1. So we would expect the predicted charges to decrease when someone is a male.
So this is the results that we received from our MLR model. And we had our actual charges from the testing set on the x-axis and our predicted values on the y-axis. And then the solid line would be a 1-to-1 ratio between those two. So in an ideal situation, all of our predicted values, which are the red dots, would fall exactly in line with the line. So we had a pretty decent model. It's not the best. All of the high values of charges are pretty linearly associated with our predictions. So yeah, this is what we got from our model.
Okay, so that completes our like human analysis portion. So now we're going to go into when we started to use AI to try and generate models for this data set. So we use ChatGPT, Gemini, and Copilot. So in order to have these AI platforms create predictive models for our data set, we had to give it a prompt, and we made sure to give all three platforms the exact same prompt to see how they responded similarly and differently. So in the box with the bullet points, this was pretty much our prompt, like verbatim. So we uploaded our training data set and we asked it to generate the best model using that training data to predict charges. And we wanted three different things. We wanted a statistical justification of why the model it chose was best. And we also wanted it to explain why each predictor variable was chosen. And then we needed the R code so that we could generate those predictions and see how well it performed. And so you might think this sounds pretty easy. We just put it into AI, it'll give us the answer, and then we'll have our predicted charges. But unfortunately, it was not that simple because AI would give us an R code and then we would run it, and oftentimes there'd be several errors. So we had to take those errors back to AI and say, please, like, fix these. And we had to do this many, many times, which is why we got a little aggressive at the end of our prompt with the all capitals. So in the box off to the side, it shows how many times we ran into this issue with each of the three platforms. So ChatGPT definitely had the most errors, and then Gemini was in the middle, and Copilot had the least. But don't let this be misleading, like thinking that ChatGPT was the worst and Copilot was the best, because we'll find out that that was not the case.
So after we completed our AI analysis portion of this, we did come up with some initial observations. And the first of which is that we noticed ChatGPT limited the amount of prompts we could ask that directly reference the data set that we uploaded. It would be about 10, and then it would stop and say that we had to wait 24 hours. We did not run into this problem with Gemini or Copilot. And then another conclusion we made is that AI also generates a black box approach, meaning that no matter how much we asked, it would not really come back with a statistical reasoning for why they did what they did. Like the ChatGPT model did include an interaction, but no matter how much we asked, it would not tell us that they did an ANOVA table that told them that the BMI and smoker interaction was statistically significant, whereas we would be able to explain our results that way. So that leads to the conclusion that AI lacks in explainability.
And then AI also was inconsistent with the R code it produced and what it thought it was going to produce. So what we mean by this is AI would give us an R code and it would say this will create a prediction model with an R squared of 0.99, which would be really good. And then we would run the code and the R squared was actually like 0.85. So this just shows that AI is very inconsistent with what it thinks it's going to produce and what it actually does. And then a final concern that we had specifically with Copilot was that it could not process large data sets. So we mentioned at the beginning that we're also working with a vehicle insurance data set, and we're not presenting on that today, but we did want to note that when we tried to get predictions from Copilot, it was simply like too large for Copilot to process.
So these are the results that the AI models end up giving us. You'll notice that Copilot and ChatGPT's predicted charges actually are really similar, even though they chose different models. It does look really similar to our own because we did choose the same model as ChatGPT. And then you'll also see that Gemini's predictions fall pretty much in line with the actual charges line. So we would tell by this that Gemini performed the best, but we'll go into the actual statistical metrics that we use to measure this.
Yeah, so here's going to be the comparison portion of our results. So we used RMSE, R squared, and MAE as our three statistical metrics to compare the models. So we're going to explain what those are. So first we have RMSE, that's root mean square error. So it basically deals with the difference between actual and predicted values, and it works with the average of the squares. And this is like our best measure of error. And then we have R squared, which if you've had a stats class, you've probably heard of it. It's a value between 0 and 1, and it represents the proportion of variance in the response that's explained by the model. And so this is also a good indicator of how well the model fits the data, but you have to be careful because as you increase the number of predictor variables you use, R squared is naturally going to increase, so this can be misleading. And then our third way of analyzing error was MAE. So this is mean absolute error. And it's very similar to RMSE, but it works with absolute values, which mathematically are a little more complicated to work with than squares, which is why we like RMSE the best. But we did consider all three when comparing the models.
Just to make the difference between these three metrics a little more clear, we're going to consider one scenario for each of them. So the scenario for RMSE is a real estate agency that wants to build a predictive model to estimate housing prices. So comparing it to ours, this is charges in our case, and then they used 4 different predictors for their model. If they were to come back with an RMSE of 100,000, that would mean that on average, the model's predictions deviate from the true prices by 100,000. So in RMSE, we like to see a lower value of that error metric.
Okay, and then an example of R squared, if we had an agricultural team trying to predict crop yields and they were using 4 different predictor variables, then a high R squared value would mean that the model explains a larger proportion of the variability in crop yields. So if we had R squared equal to 0.8, that would mean that the prediction model explains 80% of the variability in those crop yields.
And then lastly, the scenario for MAE would be a retail chain that wants to forecast store sales with those 3 predictors. And if they were to come back with an MAE value of 5,000, it would imply that on average, the model's predictions deviate from the true sales by 5,000. And so you might be thinking that that sounds a lot similar to RMSE. They're both in the same units as the predictor variable, and their explanation sounds about the same. But like Callie said, RMSE works with square root, and MAE works with absolute values. That means that RMSE penalizes large errors more heavily due to squaring, making it sensitive to outliers, while MAE treats all errors equally by averaging the absolute differences, making it less sensitive to outliers. So RMSE's penalty for big mistakes makes it better when large errors are unfavorable. And so after we did all of this AI analysis, we noticed that AI never considered a shrinkage model, or at least it didn't tell us that it did that when we asked for benchmarking against other models. And we were wondering if either a shrinkage model performed so poorly that it wasn't even worth including in the explanation, or why they didn't consider it at all. So a shrinkage model is just an improvement to the traditional MLR models, but it uses a penalty to shrink model parameters towards 0. So we chose to do a ridge regression. The RMSE is wrong there, but we'll show it on the next slide. But comparing it to our MLR model, the equation was pretty similar, but our results are on the next slide, so you'll see how that worked out for us.
Yeah, so here's a summary of our overall results. So we have our original MLR model, and then we have the 3 AI models, and we included the shrinkage one that we just mentioned. So as you can see, Gemini had the most accurate model because its error values were lowest and its R squared was highest. And then it's also worth noting that our first original human analysis model is basically identical to ChatGPT. So that was just an interesting observation we had. And then you can also notice that when we created our shrinkage model, it actually performed second best. So it's kind of interesting that ChatGPT and Copilot didn't suggest using a shrinkage model when they suggested the quote unquote best model actually performed worse than other alternatives. And so this is just a current summary of our findings as we are still working on this.
Yeah, as Kelly said, we are still working towards the end of the semester, so these are just current conclusions that we've come to. And our first one is if humans even stand a chance against AI, you have to have background knowledge in statistical modeling and statistical analysis and creating code. Because if we weren't knowledgeable about which models were best for these data sets and what the metrics are supposed to look like, then we wouldn't be able to tell if the model performs well or not. And then similarly, it would have been nice if we had a little more expertise in generating our code, because instead of going through the hassle of having all of the errors, we could have just fixed them ourselves. So that would be helpful as well. And then additionally, with one of our models on our large data set, we did do a similar model to what Gemini or what Copilot suggested for the smaller model, and it actually took over 4 hours to run the code, but ended up being like the worst performing model ever. So having the knowledge of if that statistical model would perform well based on the predictors that we were using, that would have been better. And then also similarly, reconciliation must be performed on every AI generated result, just because AI does have a track record of giving us inconsistent results like Callie was talking about before. So anytime that AI produces any metric, you have to go back and make sure that it received it the right way and that they're actually telling the truth.
And then a final conclusion we had is that AI is lacking in its consistency because we used 3 different AI platforms and got 3 different models. So there's like a loss between all the different AI platforms performing the same. And then also AI is lacking in its explainability. As we mentioned earlier with the black box approach, it simply can't explain all of its work and why it does things, which is definitely like a downfall of using AI. And so these are definitely things that like AI needs to get better at if it's going to be useful in doing statistical predictions like this. Okay, so that is the end of our presentation. Do we have any questions?
How quickly do you think AI is going to catch up?
I think that based on where AI was a year ago compared to what it's at now is a lot different. And even with every update that like ChatGPT gets, it just keeps getting better. And
Yeah,
like what
there
we
was a
saw
new
with-
one yesterday, right?
Yeah, and what we saw with the images is a year ago, AI would not be able to trick anyone on what was AI generated. So I think that if it moves as quickly as it did with generating images, then I think it could get much better really quickly. But there are still those things like explainability and consistency that it is pretty far behind on. So
So was it the Gemini that used that had the best prediction? And it was a random forest.
Mm-hmm.
Did you guys consider a random forest and discard it or not?
Yeah.
not yeah, in our initial, like before we knew what AI was gonna do, we did end up looking at a random forest model. But we likely will maybe before the end of the semester do it on our own and see if we mess around with more feature engineering, if it could produce better results than even theirs.
Yeah, I just didn't know if you didn't choose it because you weren't familiar with it or you were familiar with it and you discarded it because you didn't think it was appropriate. How did you make that decision?
Kind of like a bit of both. Maybe we didn't consider it because
There was a time constraint as well.
Yeah.
It's not because we found that it was inferior or anything like that. One thing that we are planning to do is to actually do like an ensemble prediction, sort of like you use, I don't know, 6, 7 different models, and then you take a fraction of each model's predictions and form a composite prediction, which is again something which all these AI platforms did not suggest that they did. They just went with one. Right? We totally find the best model. Like we did not say that you cannot combine predictions. So it doesn't do that either at this point. One thing to note is all this analysis is correct based off work that was done in October, November 2025. We don't know where this goes even in a few months, but this information is current, all right?
Thanks.
We don't have any other questions, and I guess that concludes our presentation.